Hello everyone. This is Unsteady Flowing Pipe Networks, and our next lecture is still dealing with unsteady one-dimensional open surface flow in prismatic channels, but today we are going to deal with the boundary conditions. But first of all, let's see where we were. So what we have is an open channel flow, okay? And mostly we are dealing with a rectangular channel, so something like this here. For the sake of simplicity. And we did steady state analysis. So what happens in the long-term steady state case? And then we also derived the famous Sandbanan equations and the shallow water wave celerity. Okay. And we also derived the differential form of the characteristic equations, which were very similar. Which were very similar to the previous cases. So essentially you have a temporal derivative and the spatial derivative of the Riemann invariant, which is v plus or minus 2c. And then you have the source terms on the right hand side that we agreed that this can be pretty complicated because now the characteristic lines are changing, the slope of them. Why is it so? Because the slope of the characteristic lines is v plus or minus c. So this term here. And on one hand, the wave celerity varies with the depth, so the c is varying, and on the other side, v cannot be neglected. So the flow velocity can be very close to the wave celerity, or it can even exceed it. So now at every grid point, the slope of the characteristic is changing, which resulted in this figure. And then we agreed that what we need is an interpolation. So at each time step, we'll have to find that left point and that right point that have the following property. If I interpolate velocity and wave celerity from the neighboring data points, so that's this point and this point, if I interpolate them here and evaluate the slope, then the slope will exactly hit the desired new point here. And I gave you a simple example how to do that, both equations, and there is an interpolation technique which is, I think, simpler. Now, today we are dealing with the boundary conditions. Now let's not forget that this will be very similar to the previous characteristic case, because what happens is that if this is your boundary, say, the right boundary, then you have only a left characteristic line entering, and if this is the other boundary, the left boundary, then you have only one characteristic line. So the basic feature that at the boundaries we have one characteristic line does not change, at least first. Okay, so what we do is we come down here for this section, boundary conditions. Okay, and let's first deal with the left boundary. So again, at the left boundary, I have one of these quantities, beta right, okay, v minus 2c. I know what beta right is, 25 or 42, whatever, but I don't know neither v nor c, so I will need another equation. Now, as long as the flow is subsonic, meaning that the velocity does not exceed the wave celerity, this is fairly simple, because I can be sure that I have one of these quantities here. So for instance, if I have prescribed velocity, that's very simple, because then v is known, so I can work out the wave celerity, and from the wave celerity I can work out the water depth. If the water depth is fixed, then it's also simple, because I can work out the wave celerity from y, and then I can work out the velocity. If I have a prescribed volumetric flow rate or mass flow rate, that means that b times y by times v is prescribed which is the flow rate, and B is the channel width. And that means that this gives me one equation here, and the other equation is the beta characteristic and the definition of wave celerity. So this is three equations of three unknowns. You can solve them typically by numerical technique, because if you try to solve them analytically, you will see that this can be reduced to a single equation which will include the third power of velocity. So that can be tricky to solve. There is still analytical solution for a third order polynomial equation, which is the Cardano's formula, but I think personally that it's simpler to solve it numerically. Again, the really interesting bit starts when you have a tank boundary condition, by which I mean that something like total pressure is given, okay? So when the flow accelerates isentropically, so lossless, from a tank water depth to the entrance of your channel, then you have the energy equation. And then you can solve this equation together with the characteristic equation, and that will give you this. So for inflow, if the tank flow rate is given, then this will be your velocity here. But as we are speaking about inflow, this gotta be larger than 0. And this is also bigger than 0 if this condition holds. So if the tank water depth is larger than this quantity. There's another interesting question. What happens if the tank water depth is so high that it reaches the inflow reaches the wave celerity, which, if you do the maths, will happen at this tank water depth value, okay? And then you also have to take that this will be the C value, and then you also have to take care of the outflow, okay? So far I've been speaking about inflow, that is subcritical inflow, so velocity is larger than the 0 but smaller than the wave velocity, and transcritical inflow when the velocity is positive but it equals the wave celerity. Now if you happen to have outflow, which is again that this condition does not hold, then as previously, you have to replace this boundary condition, which is a lossless inflow, to this boundary condition. This is pretty much the same as earlier. You're losing the kinetic energy. So now this equation is replaced by this equation. You solve again the whole problem, and then you come up with this. Okay, and this holds only if the tank water depth is smaller than this value, which is sort of nice because previously we got that the velocity is positive if you have this condition. Now the velocity is negative if you have this condition, even though the equations were different. So this is physically consistent. And then there's another issue when the outflow reaches the wave celerity, which is again, if you do the mathematics, then you will come up with this equation, okay? And beyond this point, we have to remove yt, the boundary condition, because if the outflow reaches this wave celerity, then no information can propagate backwards from the pipe, from the surroundings. So so you don't have the y boundary condition. I will show you in a minute what this exactly means. Okay, so we can put everything nicely together into a table. So probably let's start here. Sorry. So we are at the left boundary. So this is the inflow, as you see. So this is when the velocity is positive. If this condition holds, then you have subcritical inflow. So inflow which does not reach the wave celerity, and this will be your velocity. This will be your water depth, and C is always computed from the beta value, the characteristic equation. And if you reach, for the inflow, the wave celerity, then you have to prescribe both quantities. Okay, this is pretty similar to the, if you have ever done gas dynamical simulations in CFX or Fluent, it's the same as supercritical or subcritical flow. So if the inflow is supercritical, then you have to prescribe everything. If the flow goes out from the channel, then these are your working equation. You can have subcritical outflow, you have transcritical outflow. Here are the equations. Probably it's worth mentioning that if you have subcritical outflow, that you calculate first this quantity from beta and yt, and then the wave celerity and everything. But if you have transcritical outflow, then you first have to compute this quantity, and then from this, the depth, you can compute the velocity. As usually, I'm sorry. You can do the very same derivation for the right-hand side boundary condition. Okay, there's a typo here. I will correct it. It's essentially the same. You just have to do the maths patiently. Okay, so as usually, I've implemented these boundary conditions in 2 small MATLAB scripts, and I will show you some demonstration. So this is our previous code, but now I've replaced the boundary conditions with these 2 new boundary conditions, which are essentially these things that I just explained. So first I will run a simulation where on one end the water depth is 2 meters, the right hand side 2.9 meters, but the height difference is 1 meter. So if you run this, you also see that there is a nice bump within the, okay, I will not magnify it. So left boundary condition 2 meters, the red dots, red circles are the boundary conditions, the right boundary condition is 2.9 meters, okay? And it's worth seeing that, as you see, the left boundary condition, even though it's 2 meters, it's 1.99, exactly because of this boundary condition here, okay? So if you prescribe, say, 2 meters and there is inflow, then the real water depth will be something around 1.9 or so, okay? So that's why the difference is. Okay, so we have a nice flow from the left to the right. This is 3, this is 2.9. It did not stabilize yet, but the velocity is more or less positive all along the pipeline, the channel. Okay, now I will reduce the water depth on the right-hand side. Okay, and clearly what we will see is that the flow is faster. Okay, so the velocities are higher. And also we see a nice hydraulic jump here. Okay, but otherwise it's fairly nice. You see that I'm not quite running as long as I should, because the flow rate, this is the flow rate on the left-hand side, this is the flow rate on the right-hand side, 1.77, 2.84, it has not yet stabilized, okay? So under steady state conditions in the long term, these 2 numbers should be the same. Okay, I'm decreasing more the water depth. So now what we are expecting is that you have an even higher flow rate. We still have our hydraulic jump here at this location. Okay. And what I want to show, this is again the same. You see that the difference is getting larger. As the velocity increases, the kinetic energy term increases. So the difference here between this is the tank water level, this is the water level, the 1.91 is the water level at the beginning of the channel. Okay, now let's make something funny. Let's make this 0.5. Okay. And if you see here, you see that at the end of the channel, the flow velocity reaches the sonic velocity, which is the red dashed line. Okay, so as I said, we're losing the information. Okay, so we are not using the tank boundary condition anymore because the tank boundary condition is too low. Okay, so simply this is the free outflow from the channel to the tank, which is down. I could even set minus 0.5. I cannot because I'm okay. The reason is that I'm interpolating it, but I can easily manage this. So let's make it's simply a question of the initial conditions. Okay, now it will work. So now you don't see the outflow, the outlet tank height at all because it simply pours the water out. So what you need to imagine here is just a second. Okay, it finished. So what you need to imagine here is that you have a tank here and then the water level is somewhere here beneath. Okay, and it's just the water just falls into the tank. Okay, and just one last simple calculation. I will show you that the whole thing is working also backwards. So now I'm setting this to 3 meters. I'm setting the left boundary condition to 1 meter. So now the flow will be backward. It's pretty interesting to see how stable this. Okay, probably I'll have to use another inlet boundary condition because this is the initial condition should be changed. Just a second. Let's wait until it finishes. I will make this back because this is rubbish. So y boundary right. Okay, let's try this. Okay, so as you see now I have a negative flow. So the flow is flowing from the right to the left, and this is a subcritical outflow on the left hand side. And if I further increase this boundary condition, then it will be transcritical. Okay, here we go. Okay, and again you see that I more or less left the outlet boundary condition because it's not relevant anymore. So that was it, open surface channel flows and boundary conditions. Thank you for watching, and then I will come back briefly with the new material. Bye bye.